Hello, I'm Seema and welcome to part 27 of the chapter Thermodynamics. The topic of this video is spontaneity. What is spontaneity? Let us first start with a few examples. We have noticed that many things occur on their own. For example, you took birth and you kept on growing. You're not growing smaller, and nor are you going to grow younger all through your life. There is only one direction in which you are growing. You're just growing older and older and older and older and older. There's no reverse to it. Similarly, plants grow up and they only grow up, they don't grow downwards. There are other examples of spontaneous changes. For example, if you allow a gas to come into a chamber, and as soon as the gas enters the chamber through a hole, it starts expanding and occupying the entire chamber. It does not contract on its own to go back to that corner or go back into that hole and move out of the chamber. That doesn't happen. So we notice that there are changes which take place on their own. For example, hydrogen starts burning, and when it burns, you can't stop it from burning. It just burns. You've never seen it happening in the other direction. You don't see that the burnt hydrogen decides, oh no, I was not supposed to do this, let's go back to being hydrogen and oxygen. Or something is burning and the burning substance just feels that, oh, this went wrong, let's go back. That doesn't happen. Reactions occur in a certain direction, whether they are physical changes or they are chemical changes. Such changes which take place on their own with no external assistance, with no external push, they automatically just happen on their own. Such processes are known to be spontaneous processes. And this phenomenon, where you do not need an external agency to carry out a change, is known as spontaneity. So let us start with the spontaneous process. What would a spontaneous, don't we say this person's so spontaneous, he just comes out on his own. It doesn't need any push from anywhere. So a spontaneous process is an irreversible process. As I told you, when we grow up, we don't grow down. We just grow up. So it is an irreversible process, but if you want to reverse it, it has to be done by some external agency. You have to use force to carry out the opposite process. Of course, I'm not talking of growth, the biological world now, especially where growth of humans or plants and animals takes place. But if it's a chemical process and you have like hydrogen burnt in oxygen to produce water, you can turn water back into hydrogen and oxygen, but that would require energy from your side. So a spontaneous process, it can be reversed, but with the help of an external agency, not without, while the forward reaction took place on its own without the help of an external agency. 3 examples are given in the text. That heat flows from hot to cold. We've seen if you take a hot cup of tea, leave it out in the open, it gets cold. Oh, my tea is cold, I can't drink it now. How did it get cold? Because heat has this nature of traveling from hotter to colder areas. Wherever the temperature is higher, heat always moves from higher temperature to lower temperature. So heat flows from hot to cold. Gas expands to occupy whatever volume is available to it. It never contracts on its own. If it contracts, you have to push the walls together. You have to really pressurize the gas for the molecules to come closer. If you leave them on their own, they're just going to keep moving apart. Then carbon burns in oxygen to give you carbon dioxide, as I talked of hydrogen burning in oxygen to give you water. So any combustion process, when it occurs, the combustion is spontaneous, but coming back to the elemental form or the components, the reactants, is not spontaneous. If you want to do that, you will have to carry out the process by force, or you'll have to use an external agency. So how do we define spontaneity? Spontaneity is a substance having, or a reaction, a change, having the potential to proceed in a certain direction, for that change to proceed in a certain direction without the assistance of an external agency. Okay, we've understood what a spontaneous process is. And why are we talking of this spontaneity when we are talking of thermodynamics? You remember when we did the first law of thermodynamics, what did it tell us? It told us that delta U, that is the change in internal energy, is the sum of Q, which is the change in heat, plus the work done on the system or by the system. So the change in internal energy depends on the heat exchange and the work done, whether on the system or by the system in both the cases. But it does not talk of spontaneity. It does not tell us that whether the reaction would actually take place without assistance, or do we have to provide assistance for a change. Now, this knowledge is important, because if you want a change to occur, you must know, am I supposed to give it a push? Am I supposed to assist it, or is it going to happen on its own? Imagine having a hydrogen bomb and that bomb would just blow off because it is such a highly spontaneous reaction, and instead of moving away and taking safety precautions, you are out there thinking that you are going to help it happen. And if you try and help it happen at that time, initially of course you have to just start the reaction and then it goes off. Not that because hydrogen and oxygen are present in a room and they could stay there for years and the hydrogen is not going to explode on its own. The initial conditions of the reaction have to be provided, but after that the reaction is absolutely spontaneous. So our knowledge of the spontaneity of a process is important. And that was dealt by the second law of thermodynamics, which was talked about. And the second law of thermodynamics talks about a new concept, which is known as entropy. But before we come to entropy, let us come back to this topic, that is spontaneity. What do you think could be the driving force? What makes a process spontaneous? What, according to you, would make a process spontaneous? Do you remember we have been talking of a stable state, that why do electrons in an atom occupy maximum distance from each other? Because when they are at maximum distance from each other, at that point they experience minimum repulsion, and therefore that is the lowest energy state and they are stable. Whenever in chemistry we talk of stability, we always talk of a low energy state. Remember? So it means that low energy state is desirable, it is more stable, and therefore every reaction that takes place is with the intention of becoming stable. Why are you studying? You are studying so that you become stable in life later, right? So that stability is for what? All the reactions are taking place. In other words, all reactions in which heat is given out would lead to a state of lower energy, and therefore all exothermic reactions should be spontaneous, logically, right? So there are three examples here of these reactions which are exothermic and spontaneous. You have nitrogen combining with hydrogen to give you ammonia, and it's an exothermic reaction. Therefore, exothermic reactions or delta H or change in enthalpy could be a contributing factor towards spontaneity. Another example of an exothermic reaction would be hydrogen combines with chlorine to give you hydrogen chloride, and the enthalpy of this reaction is minus 92.32 kilojoules per mole, it's an exothermic reaction. Hydrogen combines with oxygen to give you water. This burning of hydrogen is also exothermic, and the enthalpy of this reaction is minus 285.8 kilojoules per mole. Now the idea is not to look at the amount of heat given out, but basically the idea is to tell you that whenever a reaction gives out energy, it automatically, according to our logic, it is acquiring more stability, and therefore such reactions should be spontaneous, and most of them are. They are spontaneous because the change in enthalpy or decrease of energy is encouraging, or it leads to spontaneity. It is a contributing factor towards spontaneity. It helps in spontaneity, right? But it was noticed that some endothermic reactions too were found to be spontaneous. Now, examples of those, let us take some endothermic reactions. They are endothermic, yet they are spontaneous. One, you take an ice tray out from the fridge, leave it out in the open. Heat always travels from a hotter body to a colder body. So the heat from the atmosphere travels into the water on its own and turns it into a liquid. But what happened in this case? Ice was at a lower temperature, but ice itself, if you look in terms of the ice, it was at a lower temperature, it came up to a higher temperature. So this is an endothermic process, yet you did not help it in any way. The heat, it automatically, the ice absorbed the heat on its own. You were not assisting it. You were not forcing. When we say assisting, you were not pushing the heat into it. You were not forcing it on it. It absorbed the heat on its own. So it was a spontaneous process. The next example is that if you put sodium chloride and you dissolve it in water, this is mildly endothermic. It's not a drastically endothermic reaction. It absorbs a little heat. If it absorbs a little heat, when you put salt in water, it should not dissolve on its own. But we find that salt dissolves on its own in water. So although it is enthalpically or energetically not favorable, yet the process is spontaneous, right? So the next example is when nitrogen combines with oxygen to give you NO2. This is also an endothermic reaction, yet spontaneous. Carbon combines with sulfur to give you carbon disulfide. This is also endothermic, positive values of energy, yet it is spontaneous. So what do we understand from this? That a reaction, when we were talking of the driving force, what makes the reaction spontaneous? So energetically favorable conditions were that energy should go down. What would be energetically favorable? That energy should go down, and that should have been favorable for spontaneity. But it was found that energetically non-favorable reactions were also found to be spontaneous. So how was that explained? That was explained by the second law of thermodynamics, which gives you the concept of entropy. What is entropy now? Okay, these reactions that were taking place, they were losing energy, yet they were taking place. Entropy is a phenomenon which is described as the degree of randomness or the degree of chaos. How much of chaos is there? It was found that reactions not only have to be energetically favorable, if they are entropically favorable, which means that if their entropy is increasing, what is entropy? The degree of randomness, the degree of chaos, the degree of disturbance in the molecules. If the molecules are just getting, their arrangement is getting chaotic, they may not be gaining energy, but their arrangement, instead of being systematically arranged, they are just here and there, wherever. That also favors the spontaneity. So now we find that there are two factors that determine spontaneity. Either the reaction should be energetically favorable, or it should be favorable in terms of entropy, or entropically favorable. And the net effect of these decides whether the reaction would be spontaneous or non-spontaneous. But that we'll come to later. Let us understand entropy further. Sometimes we find that the enthalpy change is zero. There is no heat exchange taking place, yet the process is spontaneous. You take two gases in a jar, and inside the jar there is a wall. There are two chambers, and this wall can be removed. And it's a closed jar. There is no external force, there is nothing. All we did was that in one instance we had the wall in between, and in the second instance we just dissolved the wall, or let us say it was a shutter that could just contract and remove the barrier from between. If we do that, we find that there is no energy change that occurred. There is no energy that has been put into the system. But the reaction, what happens as a result of this? Both the gases, they start mixing, the molecules, they start moving apart, and they mix with each other, and the resultant is a mixture of the two gases, and you can't tell which side has which gas, because now you have both the gases occupying the entire chamber. A spontaneous process. Both the gases diffused into each other without bothering. There was no change in energy. There was no energy being given to it. There was nothing. So energetically, it did not favor spontaneity, because energetically there was nothing happening that was assisting this reaction. Yet the change took place and it was spontaneous. So that was explained on the basis of entropy. And entropy was said to be the degree of disorder. So let me just read. S. Entropy is represented by the letter S, and a change in entropy would be shown by delta S. So what is S, or entropy? Entropy is a measure of the degree of randomness or disorder in the system. Heat and It is the degree of randomness, the disturbance. What happened in this case when ice melted at room temperature? When ice melted at room temperature, it was endothermic, it was gaining heat. And why was it gaining heat while it was energetically non-favorable? The change was energetically non-favorable because energetically favorable changes would be where the heat is going down. But ice is absorbing heat, it is gaining heat. Why? Because when it gained the heat, ice that had, the molecules had a fixed structure, they had fixed places. They are now free to flow about in the liquid state. So the degree of randomness or chaos or disturbance or disorder increased. And when disorder increases, that is a measure of entropy. It means entropy increased. And although this reaction was energetically unfavorable, it occurred because it was entropically favorable. Right? A change that is energetically unfavorable would be spontaneous if it is entropically favorable. So we understand that it is not just enthalpy which leads to spontaneity. The entropy is also a contributing factor towards spontaneity. And it is the combined effect of these two which actually tells you about the spontaneity, or which helps you to predict whether a reaction would be spontaneous or would it not be spontaneous. But that will be the topic of our next video, and that combined effect is known as the Gibbs free energy. We'll study that in the next video, but right now let us first understand this better. You know, if you heat a substance, if you increase the heat, that is, if a system is energetically favorable, you are providing heat to a system. When you provide heat, automatically the energy of the molecules would increase. And if the energy of the molecules would increase, they would start moving faster. And if they move faster, the disorder, entropy, automatically will increase. So we find that entropy depends on heat. If you're providing heat, then entropy should increase. Therefore, entropy is dependent on heat. Also, there was another thing that was noticed. When you provide heat to a substance which is at a low temperature, the entropy really increases a lot. But if you provide the same amount of heat to the same substance at a higher temperature, the increase in entropy is less. The increase in entropy is less. It means that the increase or the change in entropy is directly proportional to the amount of heat given. It is directly, but it is inversely proportional to the temperature. It is inversely proportional to the temperature. So the change in entropy is given by the formula Q reversible for a reversible change upon T, that is the temperature. And let me tell you that entropy is also a state function. And what is a state function? A function that only depends on the present state, not the path of the reaction. Whatever is the present state, in that state the entropy is fixed. So delta S is equal to Q reversible upon T. If Q reversible delta S here is only telling you about the system, so when is it that a process is spontaneous? We understood that this is entropy, a change in entropy. But when you want to talk of spontaneity, at that time we must know the total entropy change. And what is total entropy change? Whenever a change occurs, the system undergoes a change in entropy, but the surroundings also undergo a change in entropy. You remember when we talked of heat, the heat absorbed by the system has to be equal to the heat lost by the surrounding. But when we were calculating heat, we were focusing mainly on the heat changes in the system, because the amount of heat gained by the system would be equal to the amount of heat lost by the surrounding. In the case of entropy, a combined effect of the change in entropy of the system and surrounding, on the whole, if all of it together, the entropy change, let us say one is decreasing, other is increasing. But if the increase is more than the decrease, then the reaction is entropically favorable. Or we can put it in the form of an equation, that the total entropy in a change can be calculated as the change in entropy of the system plus the change in entropy of the surroundings. One of them may be positive, the other may be negative. But if the positive is higher, it means the entropy has increased, or the value of entropy is positive, or it is greater than 0. If it is greater than 0, then the process is entropically favorable for spontaneity. Then the process is entropically favorable for spontaneity. And it is, as I told you, a combined effect of both of these. That is, energetically, whether the reaction is favorable or not, and whether a reaction is entropically favorable or not. Is it energetically and entropically favorable, or is it favorable by one and not by the other? What is the combined effect of both of these that decides whether a reaction will be spontaneous or not? But before we come to Gibbs free energy, that is the next topic for the next video, let us solve a few problems that solved examples of your NCERT textbook. I'll be doing those. And before I start that, one more point let me tell you. That the entropy of a system, of a change, is maximum when it is at equilibrium. And the entropy is maximum, but change in entropy at equilibrium would be equal to 0. Because at equilibrium, it is a stable state. So, whichever direction it is, the reaction in forward direction and backward direction is equal. And if it is equal, whatever change in entropy is occurring in one direction, the opposite of that would be occurring in the opposite direction. And therefore, the change in entropy at that point at equilibrium becomes equal to 0. But at equilibrium, the entropy of the system at that point is said to be the highest. So now let us just solve a couple of problems of your NCERT textbook first, before moving on to the next video. Now before I discuss these solved examples with you, there are two examples more of entropy that I'd like to share with you. Although they're not really related to, and they're not really the best examples, yet they're the most commonly given examples. You know, your room, you try to tidy your room all the time, and you try to keep it tidy. But do you make an effort to make it chaotic, or to let it be messy? You really don't have to make an effort to allow the room to be messy, because the mess is entropy. The degree of disorder. Disorder is something that comes naturally, but order is something that needs effort. So, that your room gets messy is entropically favorable, and therefore that is spontaneous. While your tidying your room takes effort. An external agency, that is an external effort, is required to put the stuff back into its places, and therefore that is kind of non-spontaneous. Not the best example, yet it is the most commonly given example, and kids usually relate to it more. Another example of this kind is that when you're sitting in the classroom, you're all sitting at fixed places. You have fixed places, you can't move when the teacher is around. But the moment the bell rings and it is or a games period is declared for you, you just run to the playground, and then you are chaotic. Nobody knows where which one is. And that state again is from a state of order to disorder. And no teacher, you don't need a teacher to be telling you run there, do this, do that, you'll do that on your own. But in the classroom, the teacher really has to be there to monitor that each one of you is sitting at their places. So that is again an example that entropy, the change of your movement from the classroom to the playground, is entropically favorable. Disorder is likable, it is favorable, it favors spontaneity. Just two examples, although not the best, but most relatable by students. So let us now come to question 6.9. This is the solved example of your NCERT textbook. You have to predict in which of the following entropy increases, because increase in entropy is favorable for spontaneity. The first is a liquid crystallizes into a solid. What is happening to the entropy? The physical state is changing. A liquid, which is a more fluid state, where the particles can move around, they are more chaotic, while the solid state has the molecules at fixed places. So which one would be entropically higher? A liquid crystallizes into a solid. Would the entropy increase, or is it decreasing? It is decreasing. Therefore, delta S here would be negative. Delta S in this process is negative. Why? Because it is changing from a more chaotic state to a more stable, or rather a more fixed state, or a more organized state, which is entropically unfavorable. Would this reaction be spontaneous? No. Temperature of a crystalline solid is raised from 0 Kelvin to 115 Kelvin. Here it does not talk of a change in the physical state. It is, you have a crystalline solid in which all particles are at their fixed positions, and the temperature has been raised by 115 degrees, but the state is still the solid state. Then which one is entropically higher? Is the entropy increasing or is the entropy decreasing? If you are sitting at one place and you have not eaten your food, it's lunchtime and you've still not eaten food, so you slowly, in the morning when you come, you are energetic, slowly, you are at the minimum. And then comes the break, the lunch break, when you have your lunch. Let us assume that you did not move, nothing, you're still sitting on the same seat. And as you gain the energy, you were all slumped and you were tired, but as you gain energy, you become energetic. You start moving, you start playing with the person next to you. So as energy is given, although the particle in a solid state cannot move bodily from its own position, at least it can vibrate, at least it can poke its neighbors, at least it can talk to this one, play with this one, do something here, do something there. So the entropy, with increase of temperature, entropy is definitely increasing. So here delta S would be positive. For this change, delta S should be positive. Then we have this reaction. 2NaHCO3, that is sodium bicarbonate, in the solid state decomposes into sodium carbonate, solid, carbon dioxide gas, and water, which is a gas. There is entropy changing in different ways here. We had only 2 molecules in the reactant side. And we have how many molecules on the product side? 3 molecules. There are 2 kids and there are 3 students. Who is going to make more noise? Who is going to create more disturbance? 2, let us assume all of them are equally disturbing. 2 or 3. As the number of products is more than the number of reactants, molecules in the reactants, that itself is leading to more chaos, the chances of more chaos. So it is entropically favorable in the forward direction for the larger number of molecules. Why have the physical states been given? This is a solid. In the products you have only 1 solid, the other 2 are gases. And we know gases are free to move around, while solid has to sit at one place. The gases can run about. So where is the chaos more? The chaos is more on the product side and less on the reactant side. Therefore, this change is also entropically favorable, or delta S in this reaction should be positive. The next is hydrogen molecule as gas and gives you 2 moles of hydrogen atoms. Atomization is occurring. 1 molecule is breaking into 2 atoms. This is also a gas and this is also a gas. But here, what is the factor that is affecting? The number. You had only 1 mole of hydrogen here, but you have 2 moles of hydrogen atoms on the product side. The number of moles is increasing, so the possibility of chaos is more. Although both of them have the same physical state. Therefore, this would also be entropically positive. Delta S should be positive. So, predict in which of these entropy increases? Entropy increases in these 3 cases. And in the first case, entropy decreases. So now let us come to question 10. For the oxidation of iron, you have 4 Fe, solid state, plus 3 O2 in the gaseous state, giving you 2 Fe2O3 in the solid state. The enthalpy of reaction here is minus 1648 into 10 to the power 3 joules per mole. Minus means that energy is being lost by the system. The process is exothermic, right? Therefore, this must be the heat which is absorbed by the surrounding, right? Just saying. Then he has given you the entropy change for the system. And the entropy change for this reaction, when he says entropy change for the reaction, he's talking of the system. The entropy change for the reaction is minus 549.4 joules per Kelvin per mole at 298 Kelvin. this reaction is taking place at 298 Kelvin. The question is that in spite of a negative entropy change, why is this reaction spontaneous? The entropy change is negative, and we know a reaction is spontaneous only when the entropy change is positive. Or we would say not that it would be spontaneous only when the reaction is the entropy change is positive, but positive entropy change favors spontaneity. And when we talk of positive entropy change, we are not talking of positive entropy change only for the system. We are talking of positive entropy change for the total entropy change. So you are required to find out the total entropy change here. So let us do that. We know that delta S total for a spontaneous change should be equal to delta S system plus delta S surrounding. Now, delta S system is given to us, which is minus 549.4 joule per Kelvin per mole, right? And delta S surrounding is what we are looking for. So let us find out what delta S surrounding is. What is delta S? Delta S is equal to Q reversible, or for irreversible change we call it a delta H, the enthalpy, delta H, negative, and enthalpy of reaction upon the temperature at which this took place. And enthalpy of reaction is given to us. The enthalpy of reaction is now delta H for the surrounding. For the system, enthalpy is negative. Therefore, for the surrounding, this would be positive. So I write this would be equal to positive 1648 into 10 to the power 3 upon, what is the temperature? T, 298 Kelvin. 298 Kelvin. This is the temperature into 3 joules per mole. Right? When you calculate this, this comes out to be equal to 5530 joules per Kelvin per mole, right? This is the entropy change of the surroundings. So what is the total entropy change? Let us find out the sum now. So now we have delta S system and delta S surrounding. So we are calculating delta S total would be equal to minus 549.4 joules per Kelvin per mole plus, what is the delta S surrounding that we have calculated now from here? 5530 joules per Kelvin per mole. When you calculate this, this comes down to 4980, positive value, 4980.6 joules per Kelvin per mole. So the entropy change, the total entropy change is positive, and since it is positive, the total entropy change, when it is positive, it means that although the reaction, it appears to have a negative entropy here, the reaction on the whole has a positive entropy, or the reaction on the whole is spontaneous, and it is entropically favorable if you look at its total entropy. So this was about entropy and enthalpy and spontaneity. And in the next video, I'm going to bring these two concepts together in Gibbs free energy. And then we are going to talk of spontaneity actually as a whole. So if you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to all your friends, and keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.